this is another problem from chapter 3, another suggested problem from chapter 3, problem 48. 48. In this problem, exactly 3 seconds after a projectile is fired into the air from the ground, it's observed to have a velocity of blah, 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 where x-axis is horizontal and the y-axis is positive upward. So let's say that this is our ground level, and we have a projectile that's going to follow a parabola, and we are given the coordinate system. Let's put the origin here. Okay, there is no loss of generality with that. So this is going to be x, this is going to be y. They give us the directions in the problem. And 3 seconds after this projectile is launched, 3 seconds, its velocity is given. Okay. Its velocity over here is 8.6 I had, 4.8 I had. 6 plus 8 J. Again, I'm neglecting the units because we are in MKS unit system. And they're asking us, what's the horizontal range of the projectile, its maximum height above the ground, and speed and angle of motion just before it strikes the ground. So the range, the maximum height, okay, something like this, and its final velocity. Let's again use color chalk here. The final. They're asking for all these things in part A, part B, and part C over there. Okay. Now, for the range, as you know, we have a range formula, and you can try to use this, but the range formula itself requires you to end up on the same level as you started. So if you were given the velocity over here, you could use the range formula and calculate this whole range. You could be done, but you can't apply this range formula to this velocity and try to find this whole range. It's just not going to work. Right? If you apply the range formula to this one, what you're going to find is that you're going to find this range. And then, on top of that, what you can do is that, okay, it took 3 seconds to reach here, and then it will take another 3 seconds to go down. Over those 6 seconds, the x component of my velocity does not change, so I can take 6 multiplied by 8.6, and I can take this velocity, put it into the range formula, and add those two results. So it's going to be 3 seconds here, the range plus 3 seconds here, and that gives you the answer. That would work, that will certainly work. But I think it's a bit convoluted, and this doesn't really help with the rest of the problem. So another approach that will help you with the rest of the problem is to actually go back in time, which you can do. Our dynamics equations are time reversible, and find the initial velocity, and then apply the range formula. Okay, you don't have to apply the range formula, you can derive it yourself, but let's assume that this is a homework problem, so you can look it up. But if you don't know it by heart, you can of course derive it on the fly when you're solving the problem. So I'm going to go back in time. I'm going to try to find my initial velocity, even for part A. So I'll say that, so first of all, the acceleration is purely in y direction. The x component of velocity is going to remain the same. Okay, so the x component is not changing. That's going to remain the same for the initial velocity throughout the motion. For the y component, Vy is Vy0 plus Ay times delta t. This is our kinematic equation for constant acceleration motion. This is given. Vy is 4.8. This is what I'm looking for, and this is minus 9.8, and this is 3. Right? So my initial Vy is going to be Vy minus Ay delta t. This is a negative number, this is a positive number, so this whole thing with the negative sign in front is going to be positive. Your Vy0 is going to be larger than Vy. And once you find it, your Vx0 is just Vx. You can calculate the magnitude. V0 is going to be Vx0 square, Vy0 square to the square root. Though I believe for the range, you don't need the square root, you can just calculate the square of the magnitude. And you can apply the range formula. You also need to find the tangent of this angle, though. And the tangent of that angle, let's call this angle theta. Tangent theta is going to be Vy0 by Vx0. Yeah. Or, given the initial velocity and so on and so forth, you can calculate the total flight of time and multiply it by the x component of velocity. and get your range that way. You don't have to use the range formula. Okay? But this is one way. I actually prefer not to use the range formula because I don't know it by heart, and you have to take an arctangent, something like that. You can easily calculate the total flight of time and proceed that way. Let's actually do this. I'm going to, maybe I can make it fit over here. And so for the total flight of time, what we're going to do is that we start at some y0 plus we have some y0 delta t plus 1/2 ay delta t square. Now if you look at this whole motion, you start at y equals 0, you end up at y equals 0. These are both 0. Vy0 is, well, we calculated it over here. Okay? And ay is just minus 9.8. So this is the total time of flight. Let's put flight here. It's different from this delta t, or some delta t given in the problem. You can calculate the total time of flight, and then your range is going to be Vx0 times delta t flight. I think this might actually be easier than, dealing with these squares and then the tangents and so on and so forth. But both ways are, of course, perfectly reasonable. I think this is simpler. I prefer this. But if you want to do it the other way, no problem. Now, I wanted to go back in time and calculate this because it will also help me with h, the maximum height. Okay? So for the maximum height, which is, of course, measured from the ground, not your starting point, we are going to use a fact that we used many times. At the maximum height, the y component of your velocity has to be 0. Okay? This comes out of many ways, mathematically or physically, but at this point you should really know that at the maximum value of some coordinate, the velocity associated with that coordinate, to that component of the velocity, is going to be 0. Otherwise, it will just move further, you can say. Okay? So for part B, at the maximum height, y is 0, but we start with some Vy0 plus we have some acceleration. Okay? And this allows us to calculate the time. This is actually not very practical. It could work this way, but let me switch back. They are not asking about time, so let's first try the timeless formula. Vy squared equals Vy0 squared plus 2 ay delta y. This, of course, is going to be h at maximum height. This is minus 9.8. And this one is, well, something we calculated from part A, and this is just 0. So you can actually solve for h in one step. You don't have to calculate time and so on and so forth. Now, for the final part, or part C, the V final x component is going to be V0x. The x component, or I kept calling this x0, so let's call this x final. And for the y component, Vy final is going to be minus y0. Okay? Now we actually have to find the magnitude and calculate the tangent and so on and so forth, because they're asking for the speed, which is the magnitude. Vx final square, Vy final square to square root. Okay? So you actually have to carry this out and calculate the square root. And then for the direction, it's going to make some angle theta with the horizontal. In fact, it's going to be the same angle theta, so it's not accident that I use the same symbol for these two. And the tangent of that theta is, of course, minus Vy0 over Vx0. Okay. I did this way because you want to get a positive number for the tangent of theta. If I was actually measuring the theta properly from the positive x-axis, I was measuring this one, then I could actually keep Vy0, final 0. I could actually keep Vy final and Vx final, but because I'm measuring a non-standard angle in the counterclockwise direction, I actually need to keep this. Okay? So this is an angle between 0 and 90 degrees, so its tangent is going to be positive. tangent function behaves that way. I mean, just imagine between 0 and 90 degrees, both sine and cosine are positive, so the ratio is certainly going to be positive. And to get something positive, you actually need to attach a negative sign over here. Yeah, so you calculate that number, you hit the arc tangent in your calculator, and you get your answer. And that's it.